Great. Welcome back, everyone. So for today's main seminar, we have a, technically speaking, also local, but mostly residing in Oxford at the moment. This is Jakub C, and he will be talking about C-star superrigidity of virtually abelian groups. Take it away.
Thank you. And thank you for the invitation. It's a great pleasure to be able to speak here. So I want to talk about a project which is joint with Soren Knudby, Sven Raum, Hannah Steele, and Stuart White. And it's on C-star superrigidity of these groups that Aaron was talking about just a while ago. And so I should start with some broad motivation. Why we are doing this? So as Aaron said, so this is something about group C-star algebras, surprisingly. And these group C-star algebras somehow capture representation theory. And so a natural question to ask is how much data is captured in this object? Like if I start with a group and build a C-star algebra, how much of this is remembered? How many properties of the group are reflected? So somehow the motivating question is, how much does reduced group C-star algebra of G depend? So this is somehow the motivating question for today's talk. And there are some easy statements that one can make. So for example, we can ask whether this is a commutative C-star algebra or not. And this is precisely determined whether the group G we started with is commutative or not. So G being abelian, it somehow corresponds to the group C-star algebra being commutative. Right, that's one of them. Another one that Aaron already mentioned is the group G is amenable. Somehow the C-star algebra is what's called nuclear. And if you are not too familiar with nuclear C-star algebras, think of it, as Aaron said, all the different completions agree. So somehow it's an object where the completion process is somehow very rigid. And maybe let's put one more obscure one just for fun. So if the group G is ICC, meaning that all the conjugacy classes in G are either the trivial element or infinite, and this is somewhat famously equivalent to the center of this group C-star algebra being trivial. So center is the set of elements which commute with everything. And by trivial, I mean it's just the complex numbers. So this is somehow the dictionary. So some properties of the group are precisely reflected in some properties of the C-star algebra. And somehow what C-star superrigidity is about is the extreme case of this. Like, is the whole group somehow reflected in the C-star algebra? So it's somehow pushing this question to the maximum. Let's put the definition on the board. Group G is C-star superrigid if whenever the group C-star algebra of G is isomorphic abstractly as a C-star algebra to the C-star algebra of some other group, H, then we know what H is. H has to be the same thing as G. Somehow there's a unique way to build this C-star algebra as a group C-star algebra. And so what the question is, which groups do have this property that somehow their C-star algebra is unique in this way? It's quite easy to come across examples. The first group that you think of is a trivial group. And of course, what's the C-star algebra? Well, it's the span of a single complex number, so just the complex numbers. And that's, of course, the unique group that gives you the C-star algebra.
With super rigid, you just mean really, really rigid. It's not that there's two grading like in super.
This is just really, really rigid, yes. And the terminology is somehow more marketing than anything. Like, I don't know why it's not called just rigid. I didn't make it up. So the trivial group is trivially super rigid. Essentially for same reason, if you take a prime cyclic group, was the C-star algebra. What's a commutative C-star algebra of dimension P? So the group that gives this has to be abelian of size P. Well, there's only one such group. So you again get rigidity for free. And maybe last example that's not so obvious, and I actually can't prove this, but I'm being told this is true. So if G is a symmetric group, somehow the representation theory of symmetric groups uniquely determines them. This upgrades to C-star superrigidity. Because as Aaron said, if the group is finite, the group C-star algebra is nothing but the group ring that's precisely capturing the representation theory.
Small question. So do I understand it correctly? If G is a finite group, then it's reduced C-star algebra is just a group ring.
Yes, because it's the completion, but the completion of a finite dimensional vector space it's already complete. But I care about infinite groups, so this will very quickly go away. Yeah. Permutations of a finite set. But okay, so there are some examples, but there are also non-examples. So this phenomenon is not an example. Not all groups have this. So again, you don't have to look very far. Trivial group is fine, Z mod 2 is fine, Z mod 3 is fine. What's the next? Z mod 2 times Z mod 2. It's a group of order 4. What's the C-star algebra? 4-dimensional, because the group is order 4, and it's abelian. Well, doesn't give you much choice but C to the 4. Crucially, you can do the same thing with the cyclic group of order 4. Also abelian of order 4, also C4, C-star algebra. So two groups with the same C-star algebra. This, of course, is not allowed for superrigidity. And somehow this example is incredibly annoying. And all examples of groups which are not superrigid are somehow built on this observation that you can have finite groups be the same. So it's very natural to try to exclude these things if one's trying to prove that some classes of groups are superrigid. And one way to do it is to impose torsion freeness, which could alternatively be phrased as not allowing finite subgroups. So the question that most people who think about this are focusing on is the following. Is every torsion free? And this is, I think, first time this was phrased concretely was Joanna Popavaz. They have a very famous paper on group phenomenon algebras, and they remarked that in the C-star land, this is completely open and no one knows. So it's 12 years old. Turns out that it's quite hard. It's false in group phenomenon algebras. You can take LF2, so the phenomenon algebra of the free group on two generators. This is same as the group phenomenon algebra of take the infinite symmetric group, take its free pair of itself. This will give you LF2. This is by Conhan. So for fundamental algebras, this is false. For C-star algebras, it's very much open. So what's the current progress? Somehow groups permutations of the natural, well, it's the inductive limit of the finite permutations group. So it should be finite permutations of the natural numbers. Yes. This is okay. Sure. Yeah. Good point. Still false, but you need to cook up an ICC torsion-free group that's amenable. Such a group will exist, I believe. I would be very surprised if it didn't, and take a pre-product of itself, and this will be counterexample. But yes, S infinity as torsion. Okay, back to current progress. Somehow splits into two cases. So we can either talk about the amenable world, where again we have some examples of classes which are rigid. So the torsion-free abelian groups. This is Steinberg in 74. So abelian things are good. They're all super rigid as long as they're torsion-free. Some two-step nilpotent groups. This is Sven.
They wouldn't need to matter what does that talking about, right? Because the definition of superrigidity doesn't require the group to be
Correct, but I think this was in response to this question, which is restricted to torsion-free groups, right? I think that was the yes, then. Yeah. Right, two-step nilpotent groups. This is Caleb Egghardt and Sven. 2018. And then there are some free nilpotent groups. This is Traunland. And then there's us. This is crucially some, not all of them, or we don't know, virtually abelian groups, torsion-free virtually. So this is all that's known in the amenable setting. Of course, this is a very small portion of all the amenable groups. There's loads and loads which are nowhere near these things. And then there's the non-amenable groups. Well, this is probably invisible, right? Non-amenable groups. And there's a lot of progress on this. This always goes through von Neumann land. So in the non-amenable setting, all the results are corollaries of superrigidity in the von Neumann setting. And the examples of groups that you get, they usually look like, take some product of groups, pre-product with a product, them again, and then maybe you have to take an amalgam. So some groups that come from geometric group theory, they tend to look like this, amalgams of products. And then you can use Popper's deformation rigidity theory to say a lot about these von Neumann algebras, and then you upgrade to C algebras. I will, yeah.
So first of all, again, on what Philip said, again, when you ask this question for torsion-free groups, will you also ask H to be torsion-free?
No.
Okay, so then did give a valid counterexample, right? Because as Tristan pointed out, like the same.
Depending on what I'm trying to give a counterexample to, yes.
And the second question, so what was the piece? What are these like counterexamples to this?
Oh, these are examples of groups. I mean, there are groups that look like this, roughly, that are C-star super rigid. I just wanted to give something non-amenable, so at least I give you some. Oh, it's a lot of free products, a lot of products, sort of thing. But I'm not an expert on the von Neumann side of things. Right. Where was I? Right, so this is all that's known currently. Right, and I think I should maybe try to give you a hint of how proofs of these things go. So let's look at idea for abelian groups. These are the simplest you can think of, like abelian group, completely understood. So there's a old result which says, okay, maybe I should sooner. D will be now torsion-free abelian. I think G is maybe Z to the D. this is the finitely generated case, or it's maybe rationals or something of that sort. And what's the C-star algebra of such a thing? There's a nice way to describe this. It's essentially a Fourier transform. What you get is continuous functions. It's a commutative C-star algebra. It has to be commutative functions on some space. What's the space? It's the Pontryagin dual of D. So this formally is the set of group homomorphisms from G to the circle equipped with topology of pointwise convergence. It's a topological space, and you can describe the group C-star algebra as continuous functions. And there's a old result about these Pontryagin duals, which say that G is torsion-free precisely when this dual is connected. Okay, but the dual of G being connected is precisely saying that continuous functions on that thing don't have any non-trivial projections. So any projection picks off Klopen subset of your space. So this is if and only if C star RG has no proper projections. So projection is an element squares to itself, and it's equal to its adjoint. So we can detect torsion freeness for abelian groups in the C-star algebra. Now, if H is such that C star H is the same thing as C star G, and G is still torsion-free abelian, what you can check, and this is a fairly straightforward calculation, that the group of connecting components of the unitary group, the C-star algebra. So I take unitary elements in my C-star algebra. You can topologize this, induce by topology on the C-star algebra, take the connected components. Fairly straightforward calculation to show that this is actually canonically isomorphic to G. And so now if I know that the C-star algebras are isomorphic, these objects are to be isomorphic. It's unitary groups, and I know their functors. So this will be the same thing as phi naught U C star H. And again, we know that H is to be torsion-free abelian because that passes through the C-star algebra. So we recover. And so the whole what the whole equation says is that G is isomorphic to H. So what's the structure of the proof? You pass enough properties of the group onto the C-star algebra to restrict your potential H's, and then once you've restricted to a smaller class, you somehow find the group in the C-star algebra on the nose. That's somehow the meta plan. I hope this is clear. If you have questions, this is a good place to ask. Okay. Okay, let's move on then. So I'm interested in virtual abelian groups. So it's very close to being abelian, up to some finite index. Specifically torsion-free and finitely generated virtual abelian groups. So I think it's worth giving an example of such a group. Example of finitely generated torsion-free virtual abelian group. So as Aaron said, these are some twisted cross products of abelian groups by finite groups, but they also arise very geometrically. So my favorite example of this is the fundamental group of the Klein bottle. This happens to be one of these groups. So this is a very Klein bottle is a nice space. So somehow I claim that this is a natural group to consider. And in general, you can consider the fundamental group of what's called a flat manifold. There's an old theorem due to Bieberbach, which says that all of these groups, these fundamental groups are precisely these torsion-free virtual abelian groups. So there are examples coming from nature, and somehow this is my justification of this class of groups is not completely ridiculous, and there's some point in it looking at them. Okay. Theorem. This is also good to be back. And this was done in early 1910s, I believe. So this is this point ancient. So theorem say, let G be finitely generated torsion-free virtual abelian group. Then, okay, we've seen this in the pre-seminar. G is isomorphic to sums up to the D. Some twisted cross product, finite group H. But what this theorem is saying, that this is unique. So there's only one way to pick a D, pick a finite group H, and up to some natural notion of isomorphism, pick an action and pick a co-cycle. A priori, you could have two different decompositions of like this, but this cannot happen. And moreover, okay, I mean, Aaron mentioned this, but this is maximal abelian. So what, if I wanted to show that the group like this is C-star superrigid, what's my strategy? I first show that this list of adjectives is somehow detected in the C-star algebra, so that any other group with an isomorphic C-star algebra also has to fall into this class. And then I would be looking for these four pieces of data. These uniquely determine the group. So if I can detect D, theta, omega, and H in my group C-star algebra, I have recovered the whole group. Torsion-free, virtually abelian. Yes. So let's look at this. How do we get these numbers? So let's start with D. As Aaron said, the C-star algebra of something that looks like this. This is some twisted cross product of C-star algebras. And then I told you that this is continuous functions on the Pontryagin dual. And the Pontryagin dual of Z to the D is the D-dimensional torus. And now I can ask what the center of this thing is. Center, sing an R, C star R. E. This. Oh, last proposition in the pre-seminar was that this is maximal abelian as a subalgebra. So it has to contain the center. So the center is contained in continuous functions on the D torus. And now to commute with the unitaries here, it has to be the group H acts by automorphisms on my torus. And for a continuous function on torus to be invariant under conjugation means that the function is, well, it's invariant. So what I'm trying to say, omega, it's isomorphic to those functions, T to the D, which are invariant under the action of H. So they're equal on orbits of H. Precisely continuous functions. So this is essentially Gelfand's theorem when you plug in the automorphisms coming from the group H. So where can I find my D? I'm looking for a D in the C-star algebra. Well, I found it. The center is continuous functions on something that looks like a D manifold with boundary. With the lemma, E is local dimension, quotation marks. We have to be maybe a little more precise, but it's local dimension of spectrum center C star. So I've uniquely recovered my dimension from the group. Okay. This is manifold with boundary, roughly speaking. So I want to take an interior point. Yeah, maybe I should actually. Let's look at the. It's a nice topological space, and you can make sense of a dimension, and then the dimension is your D.
But will it be the split manifold?
No, this will be an orbifold. So this is not a free action. It's coming from a group action, so it always, at the level of the group, it fixes the trivial element. So once you dualize, it will be fixing the point in here, which corresponds to the trivial representation. So it always has a fixed point, so the action is not free. So you will get some you need freeness to get a manifold in the quotient. Right, so the dimension, the number D is out. Let's now try to get the group H. Some space. So to get the group H, we need a theorem due to Thoma. This is Thoma 64, I believe, which, okay, maybe we don't quite need it, but I'll say it anyways. So G be a group. Let's say G is virtual abelian if and only if something about the group C algebra. So what is it? C star G. Now it's a weird one. C star G will be a subalgebra of continuous functions on some space X, answered with matrices. So this is called subhomogeneous, but roughly this is continuous functions from the space X into and by matrices, and the group C algebra has to be subalgebra of these. So somewhat tame. So what's somehow the implication? Star G, and I will be vague here. Somehow being a subalgebra of this means that at each point you're direct sum of some matrices. At each point you have to be a subalgebra of Mn. So we can view this East algebra as a bundle of matrix algebras over X. I'm being intentionally vague here. I don't think the details are very important, but the point is C star G is some non-commutative bundle over some space X, and you can sometimes say what the space is. Right, yeah. You can have twist there as well, but you can always push it into a trivial one, but then you lose information on X. So that's clear, yeah. Okay, but here's some bundle of matrix algebras, twisted, if necessary, and then I want to get H. Where do I find H? Well, I can look at the fibers. There's a lemma. So the C-star algebra of this finite group, H, appears as a fiber in this thing. And so if I have and this is also canonical. So I have some canonical decomposition of my C-star algebra into a bundle of matrix algebras, and the C-star algebra of my finite group appears as one of those fibers. And in fact, it is the unique fiber with the complex numbers as a summand. Somehow it's canonical. You give me your group, like give me the C star algebra. I look at at this bundle, look at all the fibers. If I pick one fiber, which I see at some end, I'm guaranteed to have found the C star algebra page. The corollary, we get the C star. The fiber will be a direct sum of matrices, and then it's. So so far we have the D, we don't have H quite just yet, but we have the C star algebra of H. What's left is theta and omega. And the sad truth is that we can do any better in general, and we have to specialize to some classes of these groups to make any further progress. So what's the class? So let's assume that the finite group H is a prime cyclic group. So the immediate benefit of this is that H itself is C star superrigid. So when we here remember its C star algebra, we have remembered H itself. And G remembers. So we've upgraded remembering the C star algebra to remembering H. So we're halfway there. Now comes the scary part. This is a theorem Charlotte from 65, who has classified all of these for cyclic groups. Not quite. It's a scary bit. So if P is no more than 19, then all theta are classified. Actually, no. All right, this is coming in a minute. All theta are classified for prime cyclic groups. And now, if P is, I've spoiled it now. If P is less than 19, theta determines omega. Somehow, if your prime is small, the omega is always automatic. You don't have to look for it. I think 23 is super hard. We can't do 23. So why P19? Right? This is completely ridiculous. Why does it stop at 19? And this is some algebraic number theory nonsense. Somehow when you're doing these things, what appears is cyclotomic fields. And these things have unique factorization up until P19, and then it explodes and it becomes completely unmanageable. So number theory says, tough luck, all you can do is 19, and then have to figure something else out beyond that. And we haven't figured that yet. Right, so if we're P less than 19, then all we need to find is the action. And we know what they all look like. There's a proposition that we proved, which says that theta is actually detected in the quotient T to the D mod in this case. So this is somewhat surprising. I fix a prime cyclic group, act on the D torus, and if I know what the quotient space is, I know what the action had to be up to some notion of right somewhere. I think this is supposed to fail in general, but somehow for prime cyclic groups, life is good. Which means that we're almost done. We've now detected D, the prime cyclic group here. We now have theta because it's coming from the center. So all we need to show is that this class, all these objectives are remembered. And once that's done, we have one. So let's see that. very briefly. Let's go there. So the final ingredient, position, if G is finitely generated torsion-free virtual abelian, and H is any group such that it has the same C-star algebra, then H also has these adjectives. Finitely generated torsion-free virtual abelian. What's the sketch? Quite cute. Again, we build a dictionary for the adjective separately, and then we just use them all at once. So G virtual abelian, well, this is, we've already seen that. That's Thomas. This is saying that C star G is one of these. Torsion-free is the really hard one. And what's really surprising is that the same thing that works for abelian groups also works here. So it's, again, the lack of projections in the C-star algebra. G has no projections. This might sound easy, but this is building on some very, very complicated work regarding Baum-Kohn conjecture and similar things. So you have to understand the K-theory of the group C algebra for this, and then somehow K-naught will tell you something about the projections, and it will tell you that there's. This is due to Hickson and Kasparov. So this is the big Baum-Kohn paper they have. 7. So this is super hard, but luckily for us, they proved it, so we can just use it. And finally, the finite generation, G finitely generated. This we again detect here. I will be vague, but the spectrum of the center is manifold with boundary. The actual statement is a little more tricky, but the meta point is that it looks like a manifold with boundary. So all these adjectives are somehow detectable in the C-star algebra. So now, somehow to recap and put everything together. E is Z to the D, Z naught P, theta omega. Well, this P less than 19, incredibly annoyingly. And G is C star supergen. So how does this go? Well, we essentially have everything on the board now, so it's just collecting the results together. If H such that it's C-star algebra is isomorphic to the C-star algebra, this by this proposition, we know that H is finitely generated torsion-free virtual abelian. H is one of those, in particular by the decomposition theorem. H is isomorphic to Z to the D prime, twisted by theta prime omega prime, acted on by some H prime. But then I've told you how to recover each of these separately. So then we know that because we can see D as the dimension of the center, we can argue that D is D prime. because we can see the group C star algebra of this as a fiber. We know that C star R H, C star H prime. But of course, H is C star super rigid. So we upgrade this to H being isomorphic to H prime. So we're halfway there. Ooh, have I put too many H's on the board? I have. Aha. Yes, yes, yes. Good call. Thank you. Now it looks fine, right? Yeah. So we get the point group H, and then finally we can detect the action by the proposition over there. So we get that theta is theta prime, or maybe isomorphic to. And then finally, by Charlap's theorem, we don't have to care about the cocycle. So automatically, omega, no. But these four things uniquely determine the group. So again, we've taken the properties of the group, identified them in the C star algebra to restrict the class of groups G prime that we have to consider, and then we found the whole group. Same general idea as before. Somehow, one half of the sum virtual abelian groups that we can show are super rigid.
Ask that question?
Yes, of course. Yeah.
So when you have created the theta determines the omega, I mean, we saw in the pre-seminar that for every section,
yes,
you get two cocycles, right? So
yes.
Here, I guess what it means is that it's an omega that together with the theta gives you a cross product.
Yes, correct.
And so here, this is kind of saying that for every section, so saying, okay, you can just find one of these two cocycles such that together with theta, you get a meaningful cross product.
I'm saying that no matter which cocycle you pick, so that the extension is torsion free, you always have to have this in mind. All the two cocycles will at the end give you the same group. Yeah, this is, I should make this comment. This is a very good question. So when you do cohomology, what you're really looking at is some things that look like this. And if two cocycles are cohomologous, maybe two different cocycles give you two different extensions. And them being the same in two cohomology means that you have equality here, and isomorphism here. But it's completely possible that G and G prime can be isomorphic in a way where you don't have equality here. Maybe you can weaken this to just isomorphisms, and then you would be getting some quotient of the second cohomology group. And so what Charlap's theorem is saying, that if I care only about the isomorphism of the groups in the middle, this quotient of the second cohomology group is just a singleton. That's what's happening there. And of course, we don't care about how the normal subgroup sits in there. We care just about the subclass of the thing in the middle. I hope this clarifies this thing. Okay. I promised a little bit on Cartan, so I should deliver on that. So somehow this approach that I described is kind of limited. There's this P19 condition, which somehow seems impenetrable, and it also works only for prime cyclic groups. So the hope is to find something that just like does it on the nose and doesn't need these special cases. And the idea for that is to get inspired by the abelian case. Somehow you look at some unitaries and some connected components, and then all of a sudden the group appears. So maybe the hope is, again, finitely generated first. Generated, torsion free, virtual abelian. And maybe the group is still somehow pi naught of unitaries. Let me see some. This would be a sensible guess. Unfortunately, this fails spectacularly. You get a map, and then you have a huge kernel here. There's an enormous kernel. You more or less get the abelianization of the group. Not quite, but it's close. A lot of commutators just die here. So somehow what's the solution? This is too big. We want a smaller thing inside of the C algebra to take pi note of. So what is that something? I have to quickly tell you what a Cartan subalgebra is. Okay. See how that goes. So let A be a C algebra. B inside A massa, so maximal abelian subalgebra. And B is a Cartan. Nothing to do with Lie algebras as far as I'm aware. And people always get confused, so no Lie algebras to be found. If I'll be sneaky. I'll define something slightly different. A unitary Cartan. Now I have lost everyone. If two conditions are. So one, there exists a linear map which preserves order called a conditional expectation. One to B. So if you haven't seen this, you should think of a linear projection that has some nice properties when it comes to preserving order on the C algebra. So this is somehow easy to get. Second one is slightly trickier. So curly n of E span of this. And so the closed span of this curly n, which I will define shortly. Okay. What is this curly n? This is called the unitary normalizer. So is the set of elements U in A such that if I look at U, BU star, I land inside B. So this somehow mimics the thing that was happening with the groups, where if I took a thing in the quotient group and I conjugated my normal subgroup, I landed back inside of it because it was a normal subgroup. So I want something similar at the C-star level. And what I'm saying is that there's enough of these things, which preserves my subalgebra, that they generate the whole thing. Yes, of course, and I didn't write that. So usually you consider things in A, but I want to consider unitary specific. But this is automatic because it's unitary. Because this is an equality as well. Yeah. I can edit. I'm happy to edit. You can assume just one. It's automatically satisfies the other. Right. And now I claim that this is the smaller object, that when I take pi out of this, I'll get my group. The theorem. Originally, this is due to Sen. I guess. You all know some, no? So theorem, G finitely generated torsion-free virtually abelian. Then G is pi naught of this curly n of, and now I have to pick one of these. And if you, okay, essentially what Aaron showed is that if I look at the thing coming from the subgroup, it's maximal abelian. This is always automatic. There's not much happening there. And this is just saying that the unitaries outside of the normal subgroup, together with the normal subgroup, generate the whole group. So what we got from Aaron's pre-seminar was that if I look at the normal subgroup and the T-star algebra, it will be a unitary Cartan. So I can this now makes sense. and this is an isomorphism. Right. So now we might try to mimic this proof, but we will run into an issue. If we have some H with the same C-star algebra, we have some isomorphism between these C-star algebras, but there's no guarantee that it preserves this object. Because this is not canonical. This is coming from the explicit construction of the C-star algebra that I gave you. So we need this Cartan subalgebra, C star to the D, is unique up to isomorphism. So if we can get the uniqueness of this, then we can run this sort of analogy. Because we will know that the isomorphism between C star G and C star G prime will take one of these Cartans to the other. So this somehow motivates Cartans in C star G. Okay, and then theorem. Turns out that this is quite hard. This is some horrible object that's already difficult to understand, and now I'm asking for nice subalgebras inside of something horrible. This is going to be intrinsically horrible, but if you restrict your group enough again, you can do something. So the V looks like Z to the D. We act by just Z mod 2. So the easiest thing you can think of. And theta nice. Simplest example possible. Then this Cartan subalgebra, which is coming from my normal subgroup, is unique up to iso. This suggests that maybe it's not completely ridiculous to try to study these things. There are some evidence that it's possible to approach this problem this way, but also somehow what we've learned by doing this is that this is very difficult. One downside is that, of course, all these groups are already covered by the previous theorem. So this actually doesn't show anything new. It's just verifying the plausibility of trying to somehow appeal to this result. And in the process, what we can get, and I guess I will finish with that. For a while. Maybe I should be a little more precise. It's unique unitary Cartan with spectrum the D torus. So that's the actual statement. And last theorem that I want to mention is that if I really restrict my group, I just pick one. So let's do the fundamental group of the Klein bottle that I mentioned earlier. Particular has all these adjectives. Maybe I should I haven't mentioned this before, I think. It's Z2. Looks like this. It's essentially the simplest group that's not abelian. So if we have this group, all the Cartan subalgebras are classified. So we actually understand all of them. We have we know all of them up to the suitable notion of isomorphism. And one corollary of this is that we know all the ways the C-star algebra of this thing can arise in a dynamical manner. This is somehow the feature of Cartans. They somehow tell you about dynamical origins of your C-star algebras. So if we know all of those Cartans, we know all the ways this can arise as a groupoid, whatever that might be. Okay, and the proof of this is a horrible load of algebraic topology, essentially, because we're looking at some bundles over some space. That's what the C-star algebras look like. Now we're looking at some sub-bundles. So you do a lot of algebraic topology and out pops this thing. And I think I'll end here. Go ahead.
So here you mentioned that you should know that if this carton is unique, but also the other thing that I, as far as I understood that, okay, if you have these 2G and H, you just wanted to know that if the carton pair is this carton, the carton subalgebras are isomorphic, but they are in the form of the twisted cross product. For the ordinary cross product, we know that if, for example, the actions are the orbit equivalents, then they have a Cartan preserving one. But you checked also
I
this.
think that's going the other way, right?
No,
You're
it's-
saying, assuming the action is orbit equivalent, so we know something about the action.
Only.
Oh, it's an
Okay.
ethanol. Aha.
I think that at least for ordinary actions and even partial actions should be
Ordinary actions of what?
of the G.
Of finite groups on topological spaces? Is that the setting?
Or I think that or in general discrete groups.
Okay.
Yes, I
So,
just
the work.
wondering that's if you checked that. How about some type of the orbital?
No, we haven't thought about that, but that's a very good point. Thank you.
Okay.
Thanks. So maybe first a silly question, perhaps, but so you say that G is isomorphic to the connected components of.
Yes.
How do you? What's the group structure on like on pi zero?
So whenever you're taking pi zero of a topological group, which this happens to be, then the group structure here automatically induces a group structure on this.
Okay, okay.
So if you think about the discrete group as a discrete topological space, then all the connected components are the group elements. And
okay, thanks. And the second question was, have you actually looked at what twisted groupoid you get for these Cartans?
Yes. You get what you get. You get a twist. There's a cocycle floating around. You shouldn't be expecting untwisted things. So you have an action of, okay, we're here. Z mod 2 acting on Z squared. So dualizing, you get an action of Z mod 2 on a 2 torus. The underlying groupoid of your twist will be just the transformation groupoid. And this is conjugating one of the circles of the 2 torus. And then there's loads of twists. I haven't checked precisely what the algebraic structure on them is, but I suspect the algebraic structure should be from here. So somehow there's a cocycle, and if you multiply things, they're translated. But the interesting thing, at least from my perspective, is that the twist is a topological space. It's a circle bundle over the base groupoid. And what you get is that there's infinitely many Cartans with the spectrum of 2 torus, and you get different topological spaces being realized as the twist. And there's some mapping to I. And that's actually part of the proof here. We want to tell, like, how do you say that two things cannot be conjugated using an automorphism? Well, you show that there's something different about them. We consider the topological space coming from the twist.
Okay, thank you. Can I ask one last question, maybe? So I guess you could ask a similar question for Hopf algebras or quantum groups, right? Like if I have two Hopf algebras or quantum groups, if I just know that they're isomorphic as algebras, I could ask, are they already isomorphic algebras? Or like is the co-multiplication same? I guess that would be the. Do you know if that has been studied at all?
Well, maybe I should say that I don't really know what a Hopf algebra is, in which case it probably implies the answer to the question. I am not aware of anything. Quantum groups, I have a rough idea, but I'm not aware of anything. But how many people do superrigidity for quantum groups?
Okay.
But in the experiment, I haven't seen.
Thank you.
Yes.
Follow-up question.
So I'm interested in this cross product of groupoids. Can you sketch how this looks like?
Yes. I have to remember it. Someone shout at me if I'm doing something. Cross product of groupoids. You mean the twist, or just
Like here, these cross product were built using groups, right? And
yes.
in answering Aaron's question, you mentioned some group.
I mentioned some groupoids, right? So there's a theorem due to Renault. Wait, which says that there's a bijection between pairs of C-star algebras, where A is a C-star algebra, B is a Cartan inside. And there's a bijection between isomorphism classes of these and isomorphism classes of central extensions of étale groupoids. So things that look like circle cross unit space, to some groupoid. And these are somehow modulo isomorphism. So instead of telling you what the Cartan is, I can alternatively tell you what the groupoid model is. And this is what Aaron was most appealing to. And then it's some circle bundle, which is where my answer was coming.
Okay, but it's not saying that you're building some kind of cross product using groupoids.
Right, that's what you're asking.
Yeah.
If I have one of these, I can build a C-star algebra out of it, which looks like a cross product.
Okay, and yeah, but like algebraically, would you like is the multiplication? Can you phrase it in terms of this cross product multiplication that we have seen in the pre-seminar, like the omega appears and at the theta?
You probably can. Usually you do it with convolution algebras. So the thing that comes to mind is I would redo the pre-seminar in the language of groupoids rather than doing the groupoids in the language of pre-seminar. I don't know if someone in the audience actually know the answer to this. If I have I give you some arbitrary twist over an étale groupoid, can you build a C-star algebra in a way which resembles what we saw in the pre-seminar, which was building a cross product?
I guess
Yes.
the groupoid will not be discrete, right? You can look at these unitaries that we looked at before. But if you pretended it was discrete, then you would get similar multiplication. Right? Like where the twist is
somehow locally, right? Like you don't have like partial homeomorphism and stuff.
No, I guess. But I mean, pretended this groupoid actually.
Interesting, because this might tell us that maybe one can look for not a Hopf algebraic version of a cross product, but a Hopf algebroid version, because groupoids first. Anyway.
From
just for abelian groups. Is it saying that compact connected abelian groups are determined just by that topology? The algebraic structure is
I guess that's what it's saying, yes.
1 second.
Yes, I mean, what it's saying is that the Pontriagin dual as a topological space is enough, and then yes, I think that's.
So what was proof that we were sure?
So the original proof of this is some Czech cohomology type of argument, which doesn't really have to do much with superrigidity. And then the rephrasing, the superrigidity rephrasing is like 2000s. So I imagine the group story is much older, and this was known in the group one.
audience. If not, then let us thank Jakub once again. And this was the last seminar before the Christmas and holiday break. So we'll see you all back next year.